Hi, I'm just gonna. I was talking about. I did a little series of Kant's mathematical philosophy in his transcendental aesthetic in the Critique of Pure Reason, and essentially, what I said I was going to do after that is one more thing on him before I would move on to other philosophies of mathematics. What happened a significant amount of time after Kant died was that we have different kinds of geometries. Kant says that he uses, he talks about axioms of geometry to say different things, and how that's how we, that this is the whole idea is how we look at things. So I want to read a little thing that it's in this book here, the Shapiro book. I want to read a little thing from what he talks about here. Okay. This is Shapiro here is pointing out a little passage where Kant argues that the sums of numbers are synthetic. And then he says, it is true that one might at first think that the proposition 7 plus 5 equals 12 is a merely analytic one that follows by the principle of contradiction from the concept of a sum of 7 and 5. Yet, if we look more closely, we find that the concept of the sum of 7 and 5 contains nothing more than the union of two members into one. But in thinking that union, we are not thinking in any way at all what the single number is that unites the two, and thinking merely that the union of 7 and 5. I have by no means already thought that the concept of 12, and no matter how long I direct my concept of such a possible sum, still I shall never find in it that 12. We must go beyond these concepts and avail ourselves of the intuition corresponding to one of the two, e.g. our 5 fingers or five dots. In this way, we must gradually add to the concept of 7 the units of the 5 given in intuition. In this way, I see the number 12 arise. Thus, 5 were to be added to 7. This I had indeed already thought in the concept of a sum equals 7 plus 5, but not that the sum is equal to the number 12. Arithmetic propositions are therefore always synthetic. We become aware of this all the more distinctly if we take larger numbers, for then it is very evident that we can never find the sum by merely dissecting our concepts, i.e., without availing ourselves of intuition. What the whole idea there is that he's trying to talk against the whole idea that we can use conceptual analysis against figuring out sums like 7 plus 5 equals 12. He's saying that it's not conceptual analysis that will give us new information, but it's more intuition that will, even if it's a priori intuition. But that's mostly what I want to argue here. But what the whole question is that and I'm going to explain these non-Euclidean geometries. But do these non-Euclidean geometries destroy Kant's idea of synthetic a priori, and that for the fact that there is something that can be synthetic a priori, and furthermore that mathematics, geometric axioms, and geometry itself, which dictates how we calculate space and everything like that. Does these two brand new geometries, which are totally different from what's in Euclid's Elements, do these two new geometries of Lobachevskian and Riemann, do they destroy his idea of a synthetic a priori? Now I want to reiterate that synthetic a priori, for one a priori, means prior of experience, prior of the empirical world, independent of all that, of all the empirical things. Second, synthetic. That means it's basically the opposite of analytic, of course, but analytic is when a sentence is true in virtue of one of the words in it. For instance, bachelors are unmarried men. The word bachelor means unmarried man. So the proposition bachelors are unmarried men becomes true in virtue of the meaning of the word bachelor. Essentially, I want to look again in the transcendental aesthetic what Kant's idea of space is again. I want to look at that one more time and just sort of say it quickly, just to reiterate it, so we can think about this with respect to these new geometries. First, space is not an empirical concept that has been drawn from outer experiences. Okay, so space is not empirical; it's pure. Two, space is a necessary representation a priori, which is the ground of all outer intuitions. For instance, this cup is one empirical sense experience, which is seen and understood because it is grounded by space, and space is not itself a empirical intuition, but it's more a pure one that we automatically have, which allows for me to be able to intuit this cup and actually have a understanding of it and where it is and how I'm seeing it and stuff. Third, the apodictic certainty of all geometrical principles and possibility of their a priori construction are grounded in this a priori necessity. For if this representation of space were a concept acquired a posteriori, which is drawn out of general outer experience, the first principles of mathematical determination will be nothing but
perceptions.
Fourth, space is not a discursive, or, as I said, general concept of relations of things in general, but a pure intuition. Fifth, space is represented as a given infinite magnitude. Alright, that is all I wanted to know. That's all I wanted to know that. Okay, so what we have here, we basically characterize space as something that grounds the empirical a posteriori things that we do empirically into it. It is infinite magnitude, which kind of makes sense why space is not a empirical intuition, because it's given in infinite magnitude, so we can't really comprehend how it could be even a empirical intuition. And those things kind of characterize it. And I have a series of videos that I made yesterday, actually. I uploaded them yesterday. And those things explain. I read the whole thing. I read the whole A version of the transcendental aesthetic there. But my real thing I want to do here is now I'd like to explain these brand new geometries, which are relatively new in Western philosophy. Well, mathematics, I should say. Now, I'm going to leave a link in the bar below here to a couple of links where you can actually see what the parallel postulate is, where you can there are geometric figures which show what the parallel postulate is, what the many parallel postulate is, and what the no parallel postulate is. The parallel postulate, or the fifth postulate of the five postulates of Euclid, The fifth postulate is what has been questioned before these geometries as to whether it's analytic or not. The other four, as I have discussed, are. These, however, this fifth one is called the parallel postulate. To put it, to sum the whole thing up, it's kind of a long postulate, but to sum it up, through a point not on a line, there is no more than one line parallel to it. So we have a line, say line A, and we have a point outside of it. A point outside of it that does not intersect with line A. And thinking about this whole flat Euclidean type of geometry, you can obviously think through from your geometry classes that we've all had, of course, that there's only one line that goes through that point. Let's say point P. We have the line A, and then we have the point P under it, for example. And there's no line through this point right now, this point P. But there's only one line that can intersect that point P that will be parallel to line A. There's only one line B, there's only one line B which will be parallel to line A given this point. This is the parallel postulate. This is the fifth postulate, which is questionable as to whether it is analytic as the other ones are. And then mostly, and these axioms of geometry are essentially what Kant kind of goes upon. These are what he uses as how we represent space. And he talks about geometric axioms and things like that in the first critique as well. But and I would like to go more in depth into this mathematical philosophy of his, because this is only going a little bit deep. This might sound a little bit deep, but this is only like a little bit. And I'd like to actually, go deeper into that, but I don't know if I don't know if I'm able to do that. But essentially, the first geometry is what is commonly called elliptic geometry. It's mostly called Riemannian geometry. Now, this is the geometry of curved spheres, I guess, or curved space geometry. And basically what we're dealing with here is we're dealing with a sphere rather than a flat surface with Euclid. We're dealing with a sphere here. Now, think about the fifth postulate, the parallel postulate here. We have line A. Now, these are basically great circles going around the sphere. We have line A, which goes all the way around the sphere. Line A. And then we have line P, which is basically above it, like a bit above that line on a different part of the sphere. And basically, what the whole deal is that you can have, there are actually quite a few lines that are going to go through this point P. It's going to go through, like, for instance, like the way there's going to be lines of latitude that will go around, that will go through this, lines of longitude as well. And there's going to be various different lines that are going to go through this point, because there's so many different circles that you can have on one sphere. It's infinite. If you can imagine that. I wish I could draw that, but I don't know, I can't really. It would not be very useful. But we have so many lines that go through this one point P, and none of them are going to be parallel to the line this one line A. Let's call this line A what would commonly be called the equator on the Earth, and then there's point P, which is say in Edmonton, Canada. That's obviously north of the equator. I'm just trying to give an example so you can see it. Now there's that one line A, the equator, and there's so many different lines that can go through line P. And you can think of, for instance, I have a little drawing here. Like here you can see the line A, and then you have line point P here, and then you see this line that goes around the sphere. But that line is not itself parallel. That is not parallel to line A, because for instance it's smaller and it's a great circle, and it's not parallel. So this is what is commonly known as the no parallel postulate, because you can have as many lines go through that point as you want, and you'll never have a parallel to line A, because of the fact that you can't really do that with a sphere. You cannot have parallel things in a sphere. And now that's one kind of geometry. The other one is hyperbolic geometry, or Lobachevskian geometry. On this, we're dealing with a flat disk, kind of. It's just basically a flat disk. Now, this is, we have the whole same deal. We have line A, which basically as it's a line that goes through the middle of the disk, and then there's point P, which is basically directly above that on the disk. And as you can see, this disk here. Hopefully that kind of is good enough, but you have, first of all, many different lines that go through here, and there's a lot of the whole definition of line here is very loose, which is why there's a infinite parallel postulate. Because for instance, like this line here, this line here is the line A. Well, it says line L on here, but it's line A. And then we have this point here. This line right here is one parallel, but then we have lines that this one here is parallel, this one here is parallel, that one there is parallel, and we have, this is the infinite parallel postulate, or the many parallel postulate. So we have these two different geometries. We have Riemannian geometry, and we have Lobachevskian geometry, which make the stuff about geometric axioms, Kant says in his critique, a questionable deal. And we have basically a questionable deal about how space is represented in geometry, and we have a different this shift in this shift that is in for instance mathematics, of course, and this has, for one, it has philosophy of mathematical implications as well as epistemological implications, because this kind of sheds light on a lot of things, and it has to do with a lot more things than you would think, more than just math and geometry. One time I might discuss in more detail the epistemological implications more. But what is going on here is that, given the things that Kant says in the transcendental aesthetic and the critique of pure reason, all this stuff about space, and mostly concerned with space here, the whole things that he says about space in the section on space, are any of those things, the way that he portrays space and all that stuff, are any of those things trashed? Are his philosophies here about mathematics and about space and how geometry portrays mathematics with his, use of Euclid's elements and Euclid's geometric axioms? Are any of his philosophy about space and mathematics and geometry and how geometry portrays space, are any of those things trashed? That's a big question that many people have, is as to whether is this stuff trashed? Is this stuff more difficult to argue? Is it less reliable? Because this Kant's critique of pure reason was big in philosophy, huge, and the whole idea of synthetic a priori, in which is in a lot of his philosophy in that book, and this whole difference of this whole brand new geometries has this possibility of discounting that idea of a synthetic a priori. Now the big question here is, does it really discount that though? And you can go online and you can research this, and there are going to be people who say, yeah, it does. It makes the idea of synthetic a priori less plausible. But like I was reading through in this passage of that in this book, the whole idea here is that, with the idea of adding the number 7 plus the number 5 and summing those two units up to equal 12, there's this difference here. Is are we going to figure this stuff out through conceptual analysis or through intuition? Now, if you know Kant, you know that he will say that you won't get anything out of conceptual analysis, and you will get things out of intuition, whether a priori or a posteriori. You will get new information from intuition. Now, he says in the Critique of Pure Reason, and Shapiro discusses it in here, the fact that a priori intuition may not. It's kind of hard to understand because it doesn't rest upon experience. It doesn't rest upon empirical grounds, and it's harder to understand. But then, you think about, how do we understand the idea of space? How do we understand when we're in kindergarten and first grade how to add 2 plus 1? How do we understand those things without some kind of prior empirical experience to help us understand that? And I guess the question is, I'm not sure if that will require the person to submit to synthetic a priori and a priori intuition, but it has to, say to you that there has to be something that is given to us, or that we receive, that is given to us, or that we receive through other than a posteriori and empirical intuition. And Kant discusses in there how we gain new information through intuition, and how conceptual analysis will not get us anywhere, no more things new. And I guess because of that, when he discusses that, I'm going to look at these geometries and say that they, in my opinion, I do not think that they discount Kant's philosophy of these synthetic a priori. I don't think that they endanger that. And if they did, we would, I think that the fact that he relies on this Kantian idea of intuition saves him from being, saves his philosophy from being trashed because of these new non-Euclidean geometries. Because of his idea of intuition and the idea of a pure a priori intuition being possible, allows us to actually still hold. But I guess, so yeah, I'm thinking that, because he thinks that the only way that we can gain information is through intuition, that is going to mean that, because basically what these new geometries are different kinds of conceptual analysis, and they're not in his philosophy. They're not going to give us new information about space. They're going to be different ways of giving the same information. Basically, they're different ways of looking at the same thing. And that's the way I view non-Euclidean geometry, is that they don't. I honestly don't think that they provide new information about space. Does Riemannian and Lobachevskian geometry, do they provide us new information about space? No. They're one of them. With Euclidean geometry, we're talking about stuff basically just flat, flat planes, I guess. And then with Lobachevskian, we're talking about on a flat disk. And with Riemannian, we're talking about a sphere. So we're basically looking at space in different conceptual ways, but we're not providing any new information. And I actually believe, whether a priori or a posteriori, I think that we have some kind of intuitions about space that are given to us early, very early in life, to allow us to understand, why I can see why I understand where this cup and where it is and stuff like that. So I'm gonna go with Kant, because he's saying that that conceptual analysis gives us no more new material. That I'm gonna say that, as with many other people do also say, that these new geometries, as well, interesting and provide a new take on Kantian philosophy and make you think about Kantian philosophy, Kantian mathematics, and philosophy of mathematics and epistemology more. They don't really tarnish the idea of synthetic a priori. Given that, I guess I'm wondering, what if Kant were around, come the days of non-Euclidean geometry? I'm going to think that he would have given some much thought into it. He probably, for one, would have defended himself and would have said something about how they don't tarnish the idea of synthetic a priori. But he would also, be very interested in this, of course. But yeah, I guess that's my whole idea on that. So yeah, I guess in this little thing in philosophy of mathematics I'm doing, I'm gonna go on in this book to the big three, the logicism first, of course. But I gotta find some more papers, and I gotta find some more books online through Kindle and Google Play, and I gotta find some more text and some more resources to refresh my memory on the logicism, and then I'll get some secondhand, resourceful papers, and then I'll probably start that. So, all right, I'll see you then.